Buenos días a todos. Bienvenidos. Mi nombre es Miguel Mánica, soy el actual presidente del SMIG y les damos la más cordial bienvenida a este seminario titulado Una introducción a la teoría del estado crítico y su aplicación en la ingeniería práctica. Como muchos de ustedes saben, este es un seminario que se dividió en dos partes. Ya tuvimos la primera parte el 13 de junio y el día de hoy vamos a tener la segunda parte titulada Ensayos de laboratorio y evaluación de datos de CPTU. En general la plática es en inglés, pero tenemos traducción simultánea en español. Así que ahora ya vamos a cambiar a inglés, pero en la parte de abajo de su pantalla, ahí en el Zoom, verán ahí un símbolo con un mundito. Ahí pueden seleccionar el audio en español si así lo prefieren. Entonces vamos a cambiar a inglés. Again, welcome everybody. Today we have the second part of the talk, an introduction to critical state theory and its use in engineering practice. And today we are going to go through the part two, which is titled Laboratory Testing and Evaluation of CPTU Data. So the talk will be delivered by Michael Jeffries, that I'm sure that everyone here knows who is he and the great impact that has had in our discipline. So before moving to the talk, a few comments. Right now in the event section of the SMIC webpage, you can find a lot of material that Michael has provided us, some notes, some papers, even some spreadsheets and software that you can download. But then this will disappear after today because this is the event section of the webpage, but we are going to move all this information to the video library. So there we have both of the talks, and we will have a lot of information related to the talks. Well, so before giving the floor to Michael, I'm going to give a very brief introduction of his career. He's a senior consultant at BGC Engineering in Vancouver. He's a registered Canadian professional engineer with some 50 years of experience in offshore platforms, dams, and ground improvements. He was strongly influenced in his early years by professors Bob Gibson, Alan Bishop, and Peter Groth, of course, all ranking lecturers. Mike has pursued an interest in theoretical soil mechanics despite working as a consulting engineer. He's a keynote speaker and author at the International Conference on Liquefaction, Hydraulic Fields Construction, Engineering Mechanics, and Offshore Construction. Mike has published more than 100 papers, which have attracted more than 10,000 citations, and he is co-author of the very influential and famous book, Soil Liquefaction, A Critical State Approach. Michael is also the creator of the North-Sun Considerate model, and I'm sure that all are very familiar with it. And he has been an invited contributor to Geotechnique, and he has received many awards, among them the 2012 Cross Canada Lecture, the 2014 Sugel Lecture, and the 2018 Jennings Lecture. He was also awarded the Telford Premium Medal for Geotechnical Research in 2017. So, Michael, again, thank you very much for accepting this kind invitation and for this second part of your seminar. The floor is yours.
Right, I will screen share and hopefully can you see the screen?
Yes, we can.
Perfect. Okay, let us continue then. I always find it slightly embarrassing when I get an introduction like that, and the worst part is when it says I got 50 years of experience, which means I'm very old. So it's nice to have all the experience, but it'd be nicer still if I wasn't quite so old. But what I did on the last week was I took you through some of the ideas of critical state theory and where they came from. And then I showed you its application in a case history And what I was trying to do there was illustrate kind of the endpoint, get you enthusiastic. So what we're going to do today is we're going to fill in between the introduction of the theory and the endpoint. And I'm going to go through the details now of how we proceed and what the process is. The kind of the endpoint of theory is what I put on this slide. On the left-hand side, you have measured stress strain behavior in a triaxial test or 4 triaxial tests, which is shown in the dashed black lines. And the blue lines are the prediction of critical state theory for those tests. Now, the key thing about critical state theory is we break soil behavior really into two influencing factors. One is we have soil properties, which is things like the critical state friction angle or ratio. They do not change with stress level or void ratio. They're true properties. And then we say, actually, soil can exist over a range of void ratios and a range of confining stresses. So we have to get this second set of information, which usually we call as state measures, into our understanding of soil behaviors. And if you like to think of it, the way soil behaves is the product or the combination of properties multiplied by state measures. So we have these two things going on. In terms of the methodology, we use laboratory tests to measure properties. Because properties are not affected by structure, they're not affected by void ratio, they're not affected by stress level, we can actually reconstitute samples to determine properties in triaxial tests. And this is very convenient because when we're dealing with sands or silts, in terms of practical engineering, it is impossible to get undisturbed samples. So reconstitution with of the materials we're dealing with and then doing triaxial tests is the basis of determining properties. The second component of the process is we then have to determine the soil state, that is state parameter, over consolidation ratio and so forth. And that requires in situ tests. You cannot measure state in the laboratory because you can't get an undisturbed sample. So that's the talk today. I'm going to take you through property measurement first, and then I'll take you through state measurement second. Just to remind you where we got to last week, there are not many properties in a critical state framework. I put them on the screen here, and as you can see, there are just 6. And in fact, a couple of them don't vary very much, so you can even get away perhaps with slightly less. And this is what we're going to determine in the laboratory, is we're going to come up with these properties and what the procedures we use to get them. One of the things that comes up is you say, okay, we're going to test soil. Well, what soil are we going to test? This is an example. This is from the Cadia tailings. And within the tailings body, we have, as you can see there, a range of gradations. Whatever, we've got 10 samples we've tested for gradation and in the lab based on what we've recovered. And we have to choose. So the first thing you want to do is pick a representative gradation. And what I've sketched there in pink is kind of a line we chose. And this was our predominant gradation. And that was the focus of around testing. And you have to create a 10 or maybe a little bit more than 10 kilogram bulk sample of that gradation. So you get involved in blending and mixing or whatever to say, okay, I now have a stockpile of material that is representative of what I believe to be the average of material we're dealing with. But then you say, well, okay, but what happens if it's a little bit coarser or conversely a little bit finer? So you might wind up with 2 stockpiles or 3 stockpiles. You don't have to test each of the stockpiles as thoroughly. What we did at Cadia, we put a lot of effort into the average grading, which is like the pink one, and then we put rather less effort into what we call the step-out gradations. And we're then trying to look at what is the effect of slight changes in gradation on the properties. For example, as you go coarser, which is the brown line, you'll find the slope of the critical state lockers changes a little bit. So we're trying to assess the effect of our material type change on our behavior. And we do it by doing a program of tests for our representative gradation and then a program of tests for each of our step-out gradations. There are no, we don't do 3 tests of one gradation and combine it with 2 tests from another gradation. You have to do a suite of tests on each stockpile. Otherwise, numbers just won't add up. This is just a photograph of modern tracks or equipment. And the serious point here is how much data do you want to collect? If you go to 10% strain or 20% strain, and you only take, say, 10 measurements at each 1%, as it were, you will have a very poorly defined stress strain behavior and volumetric behavior from which to define your material properties. Conversely, if you used 100,000 data points to define it, you would have a very nicely defined curve, but the number of data points would be very difficult to handle in Excel, and it'll be very difficult to handle really realistically in any software. So you need to choose, when you set up the tests, how fast you want to scan, because this is digital. So we're making a measurement every whatever 1 second, 2 seconds, which we choose. My suggestion is that you aim for something like 2,000 scans by the time you get to 20% axial strain. That will give you a data file which will show all sorts of detail in terms of soil mechanics, but still be very easy to manipulate in Excel. And we all use Excel, so we might as well accept that and aim our procedures to what we can easily do in Excel, which preserves the detail that we're looking for. In terms of laboratory testing, we need to look at 4 things. The first, and we really need to look at them in this order. We're going to look at the critical state lockers first. Then we're going to look at stress to latency behavior. So how does it dilate in response to stress? State dilatancy, which essentially comes down to being the limit of stress to latency. And we also want to look at elasticity, because that will be important to us as well. In theory, the minimum test programs is three Traxel tests. I'm going to see if I can turn on the spotlight here now. Where's spotlight gone? No, it didn't fail to do it. Just a second. Oh, I've got my laser back. Okay, we're in business. Right. If we do test A, we make ourselves a loose sample, right, and we test it undrained. We'll get a nice static liquefaction type of failure, and that's the end point. So that's a point on the critical state line. In the old days, we tried to define the critical state lockers over here by undrained tests, and you can see how far an undrained test moves. You actually have to start over here to get to a data point over here. Well, a problem with our laboratory equipment is most of it will not go to cell pressures much beyond 2 megapascals, if as much as 2 megapascals. So it became quite difficult to define the critical state lockers for high stress states using undrained tests. But what we discovered was that if we did a drained test on a loose sample, which is this test B there, that will get quite close to the critical state at the end. When I say quite close, when you get to the end, the critical state is usually just a little bit beyond the loose drained test, and you have to make a bit of an engineering judgment as to where it might be. If I join, oops, back where I was, come on. Where's it gone? Come on. Thank you. Joining those two endpoints gives me my critical state locus. I also want to know my strength properties. Now, I can get the strength properties from the stress ratio at the end there, but at that point, I've taken a sample. At this case, I've drawn it starting at 200 kPa, and my critical state is at 20 kPa. So my transducers are losing accuracy. In the case of this test here, we're getting the critical state will be at about, well, heading towards 20% axial strain, at which point the sample is bulging, and we have a lot of area correction. So again, it gets to be uncertain. So we like to get stress to latency by putting a dense sample into the mix, and that will nicely, if we can compare test B with test C, that will give us quite a nice stab as the effect of dilation angle or dilatancy on the strength. And then finally, we need to look at how state dilatancy is. Well, once we've measured the critical state locus, we say, okay, how does the limiting dilatancy in this test match with the state parameter at which it occurs? So with these three tests, I can, in principle, get all the properties for my soil. Again, the reason I put exactly the same soil on the bottom of the slide is each of the three tests is done from the same stockpile of soil. Okay, so there's no question that the tests have got identical gradations in each one. Now, in reality, you will not get away with three tests. Some tests will not come out as you expected, or leastwise you won't get the initial void ratio. And you would also like to see redundancy in the data. So in my experience, we usually, with something like 5 to maybe 8 tests to define the properties of a soil within this framework. So how do we remold, or how do we prepare samples? I thought I'd put these together, and these come courtesy of David Reed at the University of Western Australia. And what we do is we have a steel mold, which is what you see on the left-hand photo, and that is split in two. So we put a membrane over the bottom cap, we put this mold around the membrane, and then fold the membrane down back over the top of the mold. At that point, we can now place material in it. And there are a number of techniques of placing material. What I'm showing here is called moist tamping. We'll put a spoonful of soil into the mold and then gently tap it down to make it a nice level surface, and then put another spoonful in, and we build our sample up that way. An alternative method is we make a slurry in a flask and we swirl it around, and we then just pour it into the mold. You can also drop the soil into place through air, called air pluviation. So there are different techniques. These are quite well described in the literature, and each technique can produce a range of void ratios. So in this one here, the moist tamping I'm showing you, I can vary the void ratio by changing the compaction effort. And you'll notice the compactor here, we put a stopper on it, so we can control how much we compact, and then the next layer we move the stopper, and that we do it in a very controlled manner. Once we've built the sample, we put on the top cap, and we then apply a suction. And that is what you can then, once you've got suction on the sample, you can then take the mold away, and that is what you see on the right-hand photograph. We've now got ourselves a nice, more or less uniform sample of our soil, which we're going to test on a Traxel equipment. Now, this is where we run into our first problem. what I'm showing you on the screen here is a plot of void ratio versus effective confining stress. And over here, this is the void ratio as prepared. And you can measure the as prepared void ratio very easily. You know what the size of the mold is, and you know how much, or you can measure how much soil you put in the mold. So you know the density or void ratio. The problem comes when we saturate the sample. The samples have a habit of collapsing, and we're moving water into the sample by very definition of saturating it. So if we measure the volume of water flowing into the sample, that will not reflect the volume change of the sample. You can try measuring the amount of water flowing into the confining jacket around the sample, but that's not very accurate. So the problem we ran into, and you'll run into, is that you will get very difficult to measure void ratio changes as you saturate a sample. And having saturated the sample, we're then going to consolidate it, and we will get further changes in void ratio during consolidation. And the whole basis of critical state theory is we are including the effect of void ratio on soil behavior. If we have inaccurate void ratios, we are not going to get accurate soil properties, and we're not going to get accurate predictions. So we have to make, and this is perhaps the biggest step you have to take with applying critical state methods, you have to get used to accurate measurement of void ratio. And you think of our laboratories and laboratories you're familiar with. If you walk into any of them, there'll be certificates on the wall saying they are ISO certified or got quality assurance certificates, etc. And they're using transducers with 2% accuracy on pore pressure, whatever the numbers are. But there'll be no certificate saying we can measure void ratio. Because as yet as a profession, we do not have, to my knowledge, a standard saying this is how you measure void ratio. What we came up with in about 45 years ago, and this really had to come out of Canada, is that, as you might guess from your knowledge of geography, Canada is often quite cold. We have a lot of snow. Because we have a lot of snow, we're used to dealing with frozen soils. And a lot of our testing laboratories have what we call cold rooms, which is like a freezer you can walk into. And that's how we test frozen soils. And the idea came about was, why don't we freeze the sample at the end of the test? And that is what you see on this photograph here. This is a sample that's been tested in traps of compression. We've then locked off or closed the drainage valve at the bottom of the sample if it was a drain test. If it's an undrained test, that was already closed. And we then take off the confining stress jacket, and we put the whole sample into a freezer, which is what you see there. And the idea then is, well, we're not preserving food. We only need to bring it down to something like -2, -3. But we do that, we can then disassemble the sample, which is what you see the technician doing there, take it apart, and the water stays in the sample, right? Because it's frozen. So we can take that sample, we can strip it down, and we can then put it into a very simple tray, which we put into an oven and determine its moisture content. And void ratio is moisture content times soil particle density, GS. So this technique is what we came up with, and it produces accurate and repeatable void ratios. And it doesn't matter what happens during the saturation stage. What we do is we measure the end of test void ratio, and we then work backwards using the measured volumetric strains to work out what the initial void ratio of the test was. So it's working backwards. And it looks terribly complicated, but once you're used to it, it's very easy. And depending on the equipment you're using, you may need to put it in the freezer for 1 hour, 1.5 hours. So there's a little bit of experimenting in any laboratory to work out for the tracks of equipment we've got and for the top caps we've got and the soils we're dealing with, how long we have to freeze it for, so we can strip it down. And of course, if you don't go to -18, it's very easy to disassemble it. Nothing really sticks together. So it's a very convenient method. And this demonstrates how well the method works. What you're looking at on the screen is it's a void ratio versus mean effective stress plot. And the challenge was put out by the University of Western Australia. They said, okay, guys, we want to, as an industry, see how well we can measure the critical state locus. There were 7 laboratories, actually there were more than 7 laboratories involved, but the 7 who used the freezing method, which is the method I've just described to you, got these critical state lines here, and the different color lines, and whether it's a dashed line or a solid line, indicates a different laboratory. And if you look at the bandwidth, we measure the critical state losses with a precision of plus or minus 0.02 in void ratio units. And this also means when you come to analyze tests, it's perfectly permissible to say, well, my void ratio the lab told me could have been out by plus or minus 0.02. In fact, the biggest problem here was out at the higher stress levels. That's where we got more uncertainty between the various labs. The people who did not use freezing got results that were everywhere. And interestingly, the worst university in terms of predictions was Berkeley, who refused point blank to use freezing, and their method was all over the map. But if you use this freezing technique as an industry, we can get repeatable results between laboratories. So that's that one. I'm going to talk about elasticity a bit, because we also want to pick that one up. If you haven't seen Bender elements, which is the technique we use in the lab, this is what they are. The elements are shown on the right-hand side here, and it's those little things in there and in there. What those are piezoelectric transducers, and if we put a little electric voltage on them, the element will deflect. So we can use an impulse of voltage to put a flick into the soil, and which is a shear wave, and we can measure the travel time of the shear wave. And these are, I should have said, what the guy is holding is the top cap and bottom cap of the Traxel apparatus. So we're doing this at the same time we're doing the other tests. It's almost free information. And then you get a waveform, and there's computer software that controls these things, and you see the waveform, and you pick out the travel time. And then Gmax is simply the density rho times the velocity squared of the shear wave velocity. And that's what we do in the lab, and it's very, very handy, and it's useful. Right. Let me talk to you about now processing Traxel data. Actually, we've talked about how we do the critical state. And that's basically looking at each test in turn and identifying what the critical state is and then plotting it up. For picking up the stress dilatancy behavior and the relationship between dilatancy and strength, we have to take the measurements and transform it. So on the left-hand side here, we've got a deviated stress versus axial strain graph, and we have to transform that into the stress ratio Q by P divided by P dash. So over here, I've got a Q or whatever it is, 1200 kPa. I know the P dash at the same time, whatever it was, 700 kPa, divide one by the other, and that gives me my vertical points on the right-hand graph. The second one we have to process is this is the volumetric strain graph. Here, we need to take the gradient of that graph, which is the dilatancy D. So we've got to differentiate that, and we just do it numerically. Gradient is simply 1 point minus the next point divided by, the delta x over delta y. And that gives you a stress to latency graph that looks like this. And the reason I put these eyes on here is you then need to look at that data and decide where the peak strength and the minimum dilatancy occurs. And it's minimum dilatancy because we have a compression positive convention. So D max, or maximum dilatancy, is actually the minimum value of D. and you have to pick the point out, you could say, okay, Mike, why can't we use the max min function of Excel? Well, you can, but you sometimes get spikes in the data, and you sometimes see the min and max don't necessarily occur quite at the same point. So I find it much better to look at the data by eye and say, aha, that is my point of dmin and dmax. And I do this every triaxial test, and I can then plot that data up. So here I've done that procedure, and I think I've got I've got 7 tests on the screen. And if I plot it up, this is the kind of behavior you get. And the intercept of that line with the 0 axis is the soil property M. And the slope of that line is actually 1 minus n. And the reason for the 1 minus n is because in the implementation, n is the proportion of work that goes into volumetric behavior. So 1 minus n is the proportion in shear, which is why the slope has got a value of 1 minus n. And you can see here, there's a certain level of judgment. You can twist that green line a bit, depending where your eye is. Okay, we'll come to that in a moment, at how we sort of check what we picked as reasonable. But that is not unusual data. And one of the things you'll observe, if you want to define the slope of that line really nicely, you do want some quite loose tests down here, and you also want some tests as dense as you can make them. One of the features about critical state theory is we are describing the effect of void ratio on soil behavior. To make that the most accurate process, we want to get the entire range of accessible void ratios in our test data set. If we just focused on what our best estimate of the void ratio in situ, we'd have done all our testing around here, say. Then I don't know what the gradient of that line is. So it's very important to test across a wide range of conditions. The second thing is, once we've got the critical state locus determined and fitted, we can then compute the state parameter for, go back up, on that test here. Each of those data points has a void ratio associated with it. So for each of those void ratios, I can turn it into a state parameter because I know what my P is using the CSL, and that gives me a graph like that. So I then look at this graph and say, aha, and you'll find it quite jumpy. This is, not unusual data. And what I've done here is used in my mind a thick pencil to draw a line through those data points and said, I think that is the point of minimum dilation, and that occurs at a state parameter or whatever it is, minus 0.12. So that's how we pick out the dmin and the psi at dmin, and that then gives us another plot which looks like this. So this is the state parameter at the occurrence of dmin. This is the same test data you had before, and theoretically it has to go through 0, 0. So this one now we don't have to twist the line so much because we know it must go through 0, 0, and the gradient of that line is the soil property. It's actually chi. It's the Greek letter. It's a Greek letter C, and it's chi or chi, depending which way you want to call it. And that's just the slope of the line. Now, at that point, we have determined or have plots available to us from our laboratory for us to pick up the properties we need. That is, those plots will give us M, N, the gamma and the log lambda 10, and the chi. So we're very simple. There's no constitutive model involved here. It's just taking triaxial tests and processing them in a systematic manner. And that gives us our properties. But I want to talk now and say, okay, I'm showing you graphs of stress strain behavior. How have those come about in the laboratory? Well, what we do in the laboratory, you think of a triaxial apparatus. We don't measure stress. We measure axial load. We measure cell pressure, and we measure pore pressure in the sample, and we measure displacement, and we'll measure void ratio, which is the freezing method I described earlier. But what we want as engineers is deviator stress, for example, and volumetric strain. So we need to convert what we measure in the laboratory to the values we're going to use. Conversions involve, shall I say, additional information. For example, we need to know the height of the sample to turn an axial displacement into axial strain. That's not so difficult to measure, and it can be recorded. The bigger problem is that stress, as you know, is load divided by area. Well, as the sample gets deformed, its area changes. And if the sample bulges, the area in the middle is not the same as the area at the end caps. And there are various area corrections used. There's the right cylindrical correction, there's a slip plane correction. Up to about 10% strain, it doesn't really much matter which one you use. And Bishop, who's one of the shall I say, developers of the triaxial test, he used to teach that the triaxial test was only reliable out to 10% strain. Well, as you know, if you look at our current literature and you go to any conference, everybody and their auntie is testing out to 20%. And that means when you actually look at a stress strain behavior or one's put in front of you, you can put a lot of trust up to 10%. As you go further out, you might start questioning whether the reported stress or strains are quite as accurate as they claim to be. The reason I call this slide engineering procedures is the conversion from loads and displacements we measure to engineering strains is normally carried out in the laboratory itself. You as an engineer will not be given direct measurements of load and cell pressure and so forth. The lab will, as part of their quality assured results, they'll produce a nice pretty graph and somebody will sign the graph saying this is an accurate measurement according to the standards of this laboratory. But the files they use to do that conversion can be quite large. Depends on the frequency at which measurements have been made, and it depends on how many channels of data and the format they use for their corrections. But in my experience, I have seen files as large as 20 megabytes for one triaxial test. Well, for us as design engineers or analysts, this is ridiculous to have a 20 megabyte file for a triaxial test. So what I like to do is to have what I call the quality assured results generated by the laboratory transferred to an engineering spreadsheet. And this is the format I've used over the time. It's just a very simple thing: test type, which lab did it, there'll be a project number, test date, soil tested, specific gravity, the minimum void ratio, and the post-consolidation ratio, void ratio prior to shear. And then we just get 5 columns of data. We have time, axial strain, volumetric strain, axial stress, and radial stress, which will be cell pressure for a triaxial test. It would be nice to annotate the file for area correction used. Be nice to cross-reference to the lab data sheet where the original data is held. And you might put in other comments. And these days, with cameras on every mobile phone, it's very nice to include a photograph of the failed sample, which is what you see on the bottom right. And each of these files, even if you've got 2,000 data points, that's only like 15K or something. In computer science terms, these files are very small. My own style, shall I say, is I like every test on its own worksheet. So I build an Excel workbook, and I'll have test 1 on one sheet, test 2 on another sheet, test 3. You know, Excel allows you to do this very easily, and you can put the data there. They're quite small files. You can add comments, and it gets very readable. Now, I've talked to you about how we differentiate data in terms sigma 1s and sigma r's into p's and q's. The style I like doing that is to paste in this basic data, and I put a banner across the top saying measured. So that's my import from the testing lab. What I've put over here, I've called processed. That's where I've turned those measured stresses into a mean stress, a deviator stress, a void ratio, eta, which is Q over P, epsilon Q, which is the deviatoric strain, D is the latency. Then I also use the critical state void ratio for this particular test, and then the state parameter. And this process data is what I use to generate my graphs. And you'll notice here this is taken from the spreadsheet I have provided for you as a download, and so you can look at this at your leisure afterwards. You note each test is on its own worksheet. So I'm looking at here. The tab is labeled test 2, and then I've got test 1, test 3, test 4, etc. That allows you, if you keep a standard notation, which I've got here, I can then jump in VBA from worksheet to worksheet because the names are in a sequence. So I know what they are. And that enables us to quickly look at our data in an engineering environment. So that's how we bring it together. And we need to contemplate modeling. Now, keep in mind, when I showed you the plot of strength versus the latency, you could say, well, that green line could have been twisted a bit. Why did I choose an M of 1.26? Maybe 1.28 would have been a better choice. And if I chose a 1.28, then N instead of being 0.35 might have become 0.33. So that's a very reasonable thing. But what you're trying to do as an engineer is these properties are only to get you started to assess a dam, perhaps, or a foundation, whatever you're looking at. So what we need to do is say, okay, I've looked at each test in turn, and having looked at each test in turn, I've made a first estimate of what my soil properties are for that soil. What I can do now, say, okay, if I take those soil properties and put them in a constitutive model, I should be able to recover the stress strain curve reported by the lab. So what we're trying to do is close the loop. To some extent, this process depends on the detail the model you choose provides. If you choose non-associated Moore-Coulomb, which is one of our standard models, it won't show curve behavior. Its stress strain curve is 2 straight lines. So the detail you'll get depends on which model you choose, but of course you have to face that choice as a design engineer anyway. What model are you going to adopt for your design? Most, and I put question mark, all finite element programs have what's called a soil test mode, where they can simulate standard odometer tests or standard triaxial tests. You can use the models in the finite element package you're using. If you want to, for example, use Plaxis, you can analyze your test using CHASM. You can analyze your test using Norsand. They've got I think they call it a hardening small strain model. There's a menu. You can choose which one you want, and you can then compare your simulation with your test data. My own view is it's much more convenient to do this in a spreadsheet. The only problem with doing a spreadsheet is a lot of model developers will not have provided you with a spreadsheet to do that. The spreadsheet I've provided for you, surprise, surprise, is based on Norsand. There is a version of it with CHASM, if you would want to use that, although I'd find it difficult to understand why you would wish to do that. But even though it sounds terribly complicated, you can program any of these models yourself, because what we use is Euler integration. Any plasticity model, in effect, takes your current stress state and it tells you what the tangent stiffness is. So you can work your way around a stress strain curve by saying, okay, I'm at stress level, whatever, or strain, say, of 3.5%. What is my G and K at that strain? Okay, I'll now step out by increase the strain by 0.1%, and I can use that G and K to predict my new stress state. So you can work your way around a stress strain curve. the spreadsheet you have, this is done, this is how it works. It's done in Visual Basic for Applications, or VBA. It's open code. You can look inside and see how this is done. It's slightly intimidating when you look at it, but when you dig into it, it's actually fairly simple. And this is the example of what you get. If this is the spreadsheet you're going to download, if you go to the worksheet labeled params and plots, which is what I've highlighted in pink, that gives you an interactive modeling environment. If you click on plot, you type a number in here. At the moment I'm looking at test 7. If you want to look at test 8, you just type in 8 and hit plot data, and test 8 will magically appear in these graphs. And the reason that's why we have to call these over here, we have to use the test 1, test 2, test 3, because the VBA is looking for that name. So when you say 7, VBA goes looking for test 7. And the tab names have to match. Over here, these are our soil properties. So the M, the chi, the G's, the initial state parameter are all there. And these ones in blue are the ones we've come up with from assessing, at least was the top part. These are properties we've come up with assessing our lab data. This is what we've done from the Bender elements. And then here, well, where do we get the state parameter from? Well, the lab has told us what the void ratio is. We've got our input critical state locus, and here I'm using a curved critical state locus. You don't have to limit yourself to a semi-log one. And we've used that state parameters. There we can calculate the test. You don't have to start from isotropic. You can kick in a K0 if you want to use an anisotropic test. And you can also add in a little bit of over consolidation if you'd like to. And all over consolidation does, it makes the initial part of the loading is elastic. And this is an example of the fit you should find out. And what's happening up here is, this is a test on a fairly dense sand. And it's beginning to form a shear band. So when we measure the lab, we measure the gross volumetric change and axial strain in the entire sample. What's happening in the shear band is a more intense localized behavior. The theory is running in that shear band. So the blue line is the theory, and it's not that surprising. We don't quite catch what's going on. Interestingly, we seem to do much better with the volumetric behavior. This is not unusual. We can usually get sort of much better matches out quite late time. Then as we go out here, we get into issues with area correction. And the important thing is we are more or less exactly honoring the reported test void ratio. Remember when we looked at the critical state locus and I was telling you it could be plus or minus 0.02? To best fit this test, I've allowed myself to change the initial void ratio within that plus or minus 0.02 band to best fit the test. And this is a typical result. Now, when people tell you typical, it means it's the best they have. No, this is not the best I have. This is what you should find for every test you process. If you follow the procedure precisely, and if you're not getting fits as good as this, it means some of your properties are perhaps not as good as they should be. You can then say, okay, perhaps having seen this, maybe if I got a bit of a severe mismatch bound here, I might like to go back and look at how I picked my critical state locus and see, well, perhaps I should revise that. And that's the whole process, is you can use this model or modeling to check or quality assure that your engineering assessment of what the laboratory has reported to you is self-consistent. And interestingly, at this stage, this might all seem very complicated to you, and you might say, well, I don't really understand what M does, and Mike told me how I plotted up, but what does it really mean? Well, you can use this as a video game. So you can just go and change N, go and change H, go and change state parameter, just see what happens. And what you do is you change the values here, and you just go update the model, and the blue line will change, reflecting the choices you have made over here. So, you can use this to learn. This is, in some ways, a very good way of understanding what the properties means in soil behavior. And I believe This is the approach now used at Imperial College for teaching critical state soil mechanics. They don't. In my day, we had to program it. Now they give the students a video game, say go learn what changing lambda does. But anyway, you can do that. But the serious point is this is not you're not doing this because you're going to do soil structure modeling, interaction modeling, or like this. This is your quality assurance step that your assessment of the laboratory data is self-consistent. Now, when you do this, you'll find you get sucked into it. It's very much a video game. You say, "Oh, I can tweak this. Can I do a bit better?" The important thing is you have to get equivalent fits across all the tests in front of you. Right? You can't have one that's very good and one that's very poor. You've got to adjust things so everything is more or less equivalent quality. And if you're not careful, you will lose track of what you're doing. So the technique I use, I have another worksheet, which I call fits. That's just a blank worksheet. What you do is you go back there. I grab those 4 graphs, take a copy, and then you use paste special, and you have to paste as a picture, because if you just paste it, when you change the properties, this graph will change. So you just paste it as a picture, and that captures it, right? And then you pick up a copy of those properties there, and you then paste as values to another column. So you've got a record of what properties you used to give this picture. And you go through all of your tests and you build it up. And that is the process for looking at laboratory data. One thing here I haven't got a slide for, which I should comment on. When you put a workbook like this together, it replaces it. When I started engineering, we didn't have spreadsheets. Everything was done by hand, and this sort of procedure would be written up by hand, and it would go in a calculation file. Today we're replacing old-fashioned calculation files with Excel workbooks, but that doesn't change the fact that a review engineer should be able to pick up your workbook and read it like a book. So you should put in there reference information, description of what you've done, clear graphs, and in Excel, you can happily annotate things. If you've got an uncertainty and a reason for a particular choice, describe it in the spreadsheet. So try and make it so that an engineer who perhaps doesn't know everything about your project can look at it and say, "Oh, I understand why they did that." And for those of you involved with dams, keep in mind, dams are going to be there for a very long time. And we often look back to the original data, or we have a dam safety review. So your work may be looked at by your colleague's granddaughter in 50 years' time. So keep in mind the importance of being clear in what you've done and why, and keep these images so somebody can look at them and say, "Oh, yes, I think I find those fits quite acceptable." Or, "But I can see here there's a problem with that test. Something went wrong on it." So you can pull the whole story together. So at the end of this, we have got ourselves laboratory properties. We now need to talk about in situ state and how we get that. Well, the story of getting in situ state is really the story of the electronic cone penetration test. And the U in the title comes about because when this device was first developed, it didn't have a pore pressure transducer. The pore pressure transducer came into being around 1980, and it is now absolutely standard. So what I have on the screen over here is a photograph of a tip of a cone penetration test, and then we see the internals with the internal strain gauges, and we make 3 measurements, or our basic measurements. We'd measure a tip resistance, which we report as a stress. So it's tip load divided by the area of the tip, which is conventionally called QC. Just behind the shoulder of that cone, we have a porous ring with connected to a pore pressure transducer. That location, by convention, is called U2, and that's where we measure the pore pressure. And then we measure the stress on the side of the thing, the friction sleeve, FS. Those are our three basic measurements. It's very common these days. We'll also measure the inclination of the CPT, and we'll sometimes measure the temperature inside it. So there may be more data than just these three data channels. And we push it into the ground at a standard 20 millimeters per second, and we do that hydraulically. When this equipment was first developed, and when I say first developed, we're really talking in the 1970s, we just had strain gauges down the hole or in the tip, and we had millivolt signals coming up the cable, and it was very easy to get corrupted signals. We had a lot of trouble with what we call drift, where the signals would change because of a temperature or something. These days, it's virtually standard. If I say virtually, it should be standard. I believe it is standard that inside, back where we were, inside the equipment, and it's usually just behind the transducers, we will have a microprocessor, and that will compensate for temperature. It will compensate for any twist in the device. It will do an internal analog to digital conversion. So we transmit the data digitally, which means it doesn't get corrupted. And of course, it goes into a computer. And the reason that I put this particular photograph and this particular computer on the slide is this was equipment I had built for me in 1982. And this is the electronic engineer who did it, and it's still made by Geosystems in Sweden. And he was my electronic engineer, and this was the Hewlett-Packard equipment where we recorded everything on. And it was in the old days of floppy disks. But that was the start in 1982, and everybody has followed what we started. This kind of thing is absolutely routine. Now, that's the electronic side. The question is, how do you push it into the ground? Well, this is down in Australia, and this is out on a tailings impoundment, and it is quite common to put the CPT equipment in a truck, which is what you see here, and the equipment will be operating in the middle of the truck, and we can push it into the ground, and we push it using steel rods and a hydraulic ram, and we can sit there in comfort, drinking coffee, and watching the computers, and we can have a nice air conditioning system. So it's a very comfortable way of doing work. And this is very common. This is, cone testing trucks like this, they're worldwide. However, you'll find when dealing with tailings, and you see here we had to push out, effectively make a road so we can get the truck out there. We don't always have the ability to do that. So the question, and I should say, one of the reasons we use a truck, it takes quite a lot of force to push a cone into the ground. If you look at a cone, they're often quoted in terms of their capacity. So people will say, well, this is a 20 megapascal cone or a 50 megapascal cone. That 50 megapascals is the maximum stress the cone is rated for on its tip. That actually equates, if you multiply out the size of the tip, that equates to 5 tons. So you have this piece of steel, which is 35 millimeters in diameter, and it's got 5 tons on it. So you need at least 5 tons to push a 50 megapascal cone into the ground. But it's pushed into the ground by steel rods. The soil moves against the soil rods, and you get a lot of friction. So if you want to push into fairly dense ground and you're using a 50 megapascal cone, you actually need something like 10 tons or 12 tons of reaction to be able to push the cone into the ground. You can, of course, push a cone, and when you get to a point where you can't push it any further, you can pull the cone out of the ground, use a borehole to put a casing down to where you stopped, and then, of course, you no longer have rod friction and you can restart. But that is a bit of a pain, and it slows everything down, so we try and avoid it. This business of drilling to create a hole so the cone can advance in the North American phrasing is we call it a drill out, which is on the bottom of the screen. But that's what we mean is if we got stuck, we drill a casing so we can continue the CPT. So for sands, my rule of thumb is you've got to need at least 5 tons of thrust, and you probably need more. Clays are interesting, and silts are even interesting as well. You can often get away with 3 tons of thrust or thereabouts. And that's very convenient for tailings, because if you keep in mind, perhaps the reason you're listening to this talk, you're more interested in liquefaction. Well, liquefaction is associated with softer and looser soils, and they, in particular silts, if we're in the tailings business, and they're much easier to get a cone into the ground. So this is an example of what we would call doing CPT testing using available resources. So there we have a little hydraulic ram actuated by a hydraulic pump over here, and that's doing my CPT, and I'm using this excavator to provide the reaction to that hydraulic frame. So that's how I'm able to do CPT testing. And you see now doing this, I'm using available construction equipment, which is probably on site, and I'm using a hydraulic frame. I can put that in the back of a pickup and move it to the site. It's hand portable, and this is not unusual. And here's another example. Rather than using a hydraulic excavator, we've used tanks which they have chemicals on a mine. This is a tank we've had chemicals delivered in. We've now just filled it up with water and put it on a platform. So we're using water ballast to give us the reaction so we can push the CPT into the ground. And we're out onto our tailings, very loose tailings, and we're managing to do that with only about 0.5 meter of crushed rock to get out onto the tailings. And this is just kind of an example that if you get yourself and say, well, I've got to go cone testing, you don't necessarily have to use a big cone truck. There are other ways of getting reaction, and it's reaction that really controls what you do, because the electronics will remain the same. We're using the same recording systems into a laptop computer these days. The only thing we don't show on the screen, if you're out on a tailings thing, computers don't like bright sunlight and they don't like rain, so you need to perhaps have a small cabin or something like that, or sometimes we work in the back of the pickup truck with the air conditioning running. It's all very doable, and it's the nice thing about the CPT. It's continuous, or we take a reading commonly every 20 millimeters, it doesn't matter which contractor you use. We can jump from one to another. We will get the same measurements. And of course, if you need to go into a tailings pond, we can use little jack-up platforms, which is what you see here, and we're happily cone testing there. Of course, the people who are proponents of the standard penetration test say, well, the advantage of the standard penetration test is you get a sample. Well, you can actually get a sample with the CPT, and it's called a MOSTAP sampler, and that's the photograph on the right. What it is a small piston sampler that is pushed into the ground using the CPT rig, and it's got a little liner inside it, which is what you see. And what we do is you push it down like a cone to the test depth. When we get to the test depth, we lock off the piston, push ahead, and we've got ourselves a sample. Of course, you've got to go, it's like a piston sample. You only get one shot at it, but that's the way we can do it with a CPT rig. Now, how many CPTs? Well, it's up to the engineer of record's judgment, because they're the engineer of record. It's for them to decide what is appropriate for the facility they're looking at. There are, leastwise to my knowledge, my experience, there are no real standards telling you how many you should do or what spacing you should use. You should have a geological rationale. In a case of a tailings impoundment, where is the spigot point? Where do you expect to find the slimes? Where do you expect to find the sands? And you're probably more interested in the slimes than the sands. So you can use things like in tailings. It's quite staggering how much information is captured by satellites. For not very much money, you can probably get a record of deposition activities at the site you're looking at for the last 20 years. And if something goes wrong, you better believe somebody will get hold of those records. So, you can go to photographic imagery and say, okay, let me form my judgment. This document I put on the right of the slide, site characterization for dam foundations. This came out of the Mount Polly failure, where the review board effectively said that professional engineers in British Columbia will questionably be incompetent, and they were in need of guidance. So the Association of Professional Engineers responded by getting a group of engineers together to write this guidance document, and it's public domain. It's not something you have to be a member of the association to get your hands on it. For my taste, it was written by geologists, not engineers. So it has far, far too much discussion of geology and far too little understanding of what a CPT is measuring and what it might be telling you. But it's one document out there. You should make a written assessment of your geotechnical considerations, what you're testing, where it is, and why you're testing it, with a simplified cross-sectional plan. This does not have to be a major report. You know, a 5-page memo will be sufficient, but you do need to, both for your own thinking and as part of a quality assurance program, you should produce a document saying this is what I believe are the issues, and this is my testing program, and this is what I'm doing it. It clarifies the thinking to put it into writing. I'm now just going to take you a couple of examples. This is in Portugal. It's a tailings impoundment, and by memory, it's about 3 kilometers across there, to give you a scale of things. And the main dam is here, and the main dam is about 24 meters high. The scheme was, this was originally spigoted from over here with the slimes down in front of the main dam, and we have close to something like 80% perimeter containment, so it's on a fairly shallow hillside. And then what we're doing is we're stacking thickened tailings on top of the original tailings, which is what you see going on here. And we've had a number of campaigns of testing. We had a campaign in 2008, another campaign in 2012, and then we had a campaign in 2015. This is the 2015 things, and the various colored things you can see are CPT soundings. And the big concern was, what did we have in front of that main dam? So we have these tests looking down there to the tailings in front of the main dam. We actually wanted to get into there, but we weren't able to do that at the time. That was deferred to 2018. But you say, well, that's an impoundment 3 kilometers, whatever it is, wide, and I've only got, 15 CPTs on the slide. Well, keep in mind, on this impoundment, I'm coming on top of 2 earlier campaigns. So this is not brand new data. This is building up from what we had before. So it's adding information, how things changed, how things progressed. This is Cadia. Our dam is 80 meters high at the highest. There's 1 kilometer for scale. And you can see here the CPTs are in green, and they're done in pairs. We go upstream into the tailings itself, and then we do something from the dam crest or 1 berm below the dam crest. And then the blue circles were sampled boreholes. And you can get a feeling for the spacing again. And again, we're building on earlier campaigns. We had a campaign in 5 and a campaign in 13. This is tests in 17. And that's not unusual. In fact, I'd say it's usual. Brumadinho, plan of the dam, and there's taken from their report. The CPTs, if I can find them, there's one there. And you can look at them. They actually put a lot of standard penetration tests in there, and that was just a simple waste of money. You will not learn anything of any value from the standard penetration test. The money should have been spent on CPTs. So in terms of how many CPTs, my suggestions would be this. We've got to come up, how many design sections are we going to have to characterize stability? In a small project, we may have 1 design section going through the main dam. They may want to step out a couple of sides. We may have smaller dams in another place. But we need to say, okay, how many design sections am I looking at? On any given section, my suggestion would be you need 4 to 7 CPTs. You want something starting near the toe, make sure you've got the foundation, and then you probably at mid-height of the dam, then crest of the dam, and then you need to go upstream beyond the crest. How many design sections? Well, it depends on your variability in the impoundment geometry. What I've seen over my career is a lot of engineers have gone for something like 250 meters spacing between adjacent CPTs on tailings dams. What I suggest, what I've done, what I suggest you do, is you keep copies of case history papers. We have tailings conferences. Somebody will stand up in that conference and say, here's a reporting of progress on this impoundment, or this is how we analyze this other impoundment. Those case history papers give you a precedent so you can explain your judgment and say, oh, well, this is what they used over there. My conditions are slightly different. But build that kind of stuff in your own personal file so that when people ask you, why are you doing this? Well, I'm influenced by this, or I've been influenced by that. And don't forget, you started out with a memo describing what you're trying to do. So you're building up a professional background to your work. So that's how many CPTs. Right, my favorite subject, dissipation tests. Important point, and that's why I put it in bright pink, is you get the piezometric regime wrong. Everything else will be wrong. And it will rarely be, in tailings, it will rarely be hydrostatic. So you're going to have to measure it. Now, there are two ways of measuring things. You can use piezometers, or you can actually use the CPT itself effectively as a piezometer. If you have clear sand layers in a CPT profile, then the CPT will be drained, and the U2 measured can actually be used as an estimate of the piezometric regime. Even if you're doing that, I like to do a few dissipation tests. That is a dissipation test. This procedure with the CPT is we push it a meter, and then we have to add another rod on because the rods are in meter lengths. So when we stop to add a rod, we keep logging the pore pressure. And we keep logging the pore pressure until we say it's an equilibrium value. That's called a dissipation test. And I like to have at least a couple of those on a profile because then there's no argument what the piezometric pressure was at that location. Things get more complicated when we're dealing with silt and clay strata, and they get more complicated in a lot of tailings impoundments because we may have under drainage and we may have perched water tables. My own preference is to do 1 in 4 soundings or something like that with quite a few dissipation tests in that sounding. I have one colleague, and that was out at Samincor, and there we felt the situation in front of the main dam was really rather important, a little bit like Brumadinho. And we did 1 CPT in a standard way, and then we stepped over 1 meter, and they did a dissipation test every 2 meters of depth, just on that particular CPT, and just to benchmark the piezometric regime. And of course, you've got the option of installing piezometers. And don't forget, a CPT rig can push in piezometers. And piezometers are essential for long-term monitoring because everything you see with a CPT will be what is there today. You might want to know, as the year goes on, are the pore pressures declining, or are we being influenced by infiltration? So there's often a case you should kick in some piezometers with a data logger so we can measure frequently and routinely to document how the piezometric regime evolves. And here's an example. There in blue is my dissipation tests, and you can see we've got ourselves a perched water table here, and I've got myself severe under drainage down here. This is a different thing. This was in Guatemala, where we had very rapid placement of slimes tailings. And when we do dissipation tests, the pore pressures are well above hydrostatic. The stuff is not fully consolidated yet and still consolidating down. Okay, now normalizing data. Why? Let me just have a quick slurp here. what you're looking at on the left-hand side is a CPT sounding, not unusual. What you can notice is the values are increasing with depth. We're looking at tip resistance, pore pressure, or friction. Vertical effective stress increases with depth. Soil strength and stiffness increase with confining stress. So the CPT response depends on strength and stiffness. So the CPT is going to have changing patterns with depth. And that's what you see there. So we need to take the effect of that stress level change out of our processing of the CPT data, because that's not telling us about the soil properties. We want the soil properties, in effect, are the deviation from that linear trend line is what's telling us what the soil is doing. So that's what we need to focus on. So how are we going to do that? Well, we turn it into what's called dimensionless numbers. The tip resistance, which is conventionally called QT, and the subscript T is because we have corrected it for, you remember we have the sensing element for piezometric pressure behind the tip. Well, that means some pore pressure acts on the back of the tip, and we need to add that into the tip load. So the convention is QC is what we actually measure, and then QT is that QC which is now being corrected for the measured pore pressure on the back of the tip. And we convert that QT to a dimensionless ratio, which is in standard notation is the capital letter Q, and the formula is on the right-hand side. So what we do is we take our tip resistance, we remove what amounts to the buoyancy effect from confining stress, and then we normalize it by the vertical effective stress at that depth. And because in theory we should actually be using the mean effective stress, but because K0 is such a difficult challenge for us, the convention is we use sigma V there, and the naught subscript means that's the vertical effective stress prior to the CPT going into the ground. So that, and if that is in megapascals, that will turn into just a stress ratio. If you come from a background of deep foundations, that Q is the same thing as the bearing capacity factor NQ in the design formula for a pile. The friction sleeve, we measure FS. The standard dimensionless number is over here. We divide it by that term there. So we're normalizing it by the tip resistance compensated for the buoyancy component of the confining stress. RF, which you sometimes see in the literature, that is simply the ratio of FS to QC. The problem with that ratio is that it's not allowing for the effect of the vertical stress there. So F is the standard notation. F and RF are not the same. If you're in silts or slime tailings, they can differ by a factor of 2. So you need to be careful what's being used, and that's the one you should be using. We measure the pore pressure behind the tip. Sometimes that's called U subscript C for UC during cone penetration. The convention is we measure it at the shoulder, and the shoulder is called the 2 location because when we started out introducing the piezo cone, we had a sensor location in the middle of the sharp pointy bit of the cone, and that was called the U1 location. But that location more or less measures the pore pressure induced by the compression load, not the shear component. So people became very keen on measuring behind the tip, which is now used as the U2 location, and that terminology is called B sub Q. And you can think of that if you do a triaxial test, you'll compare the pore pressure in an undrained triaxial test with the undrained strength Q, U over SU. Well, this is more or less the same idea because this QT minus sigma V is an approximation of the undrained strength. So that's what we're up to. And that with those 3 measures, we've got some numbers now which we can work with on our CPT. So issues, of course, is, okay, we've got to calculate sigma V. So what depth below ground surface did the CPT start? It doesn't necessarily have to start at the ground surface. Somebody may have dug a hole because you, for example, have gravel. So you use an excavator to dig down a couple of meters and CPT starts 2 meters down. So you need to be a little bit careful as to where you're starting. Of course, where is the water table? We're going to do piezometers, aren't we? Yes. Then, of course, what are the soil and water unit weights? Again, it's very conventional to use a single soil unit weight for a sounding. That is started out when we were doing soundings of 10 or 15 meters, and it's really perfectly adequate. When we start doing these soundings now in tailings, when we're down at 90 meters or 100 meters, you really should be thinking about perhaps how is that soil consolidated? Is the unit weight at 60 meters the same as the unit weight at 12 meters? And indeed, is the unit weight, if you're dealing with sands and silts, is the unit weight in the two strata the same? Water I put in because you've got chemicals in the water, the water unit weight may not be 9.81. And the key thing is you're adding in external knowledge. The CPT, when we push it into the ground, we data log it. There's no argument about what we've measured. But as we turn it into dimensionless numbers, we're now adding in external knowledge to compute these dimensionless ratios. And again, you need to document those and have a good rationale for what you're doing. Okay, next thing. Soil type identification. The basic use of the CPT, or was, to look at soil layering. You don't ever get high tip resistances in clays, ever, nor do we get high friction ratios in sands. So the idea was perhaps we can relate what we measure with the CPT to soil type. And various charts were developed doing this. A better framework, by the way, is we actually add in BQ. So we're going to use this Q1 minus BQ plus 1. And if you multiply it out, it just means we're using the water pressure measured by the cone in the formula. And what you get is a chart like this. This is what our Q1 minus BQ plus 1 becomes our vertical axis. Our friction ratio F becomes our horizontal axis. And I've highlighted over here, I'm looking at a particular layer. And I'll highlight in blue, you can see it's more or less constant friction ratio, and it's fairly constant BQ. In fact, I probably should have brought it into 2 layers, because I might say there's one layer there and there's another layer down here. But anyway, I've just done it as one layer. And it will plot over here like that. So each one of those data points in that part is now plotting on this chart here. And the chart is annotated for clays and sensitive soils, clays, silts, silty sands, and so forth. And what you get is, in effect, an orthogonal system. These curvilinear lines here represent changing soil type. So we go from up here, gravelly sands, as we go diagonally down across the diagram, we're moving into clays and very sensitive clays. Moving perpendicular to those soil type lines, we have effectively state parameters. As we move up here, we're getting to the more over-consolidated or more dilating soils. As we move down here, we're moving into the very contracted soils. And that green line on this particular chart represents the potential for flow slides. Any data that plots above that green line, you may get liquefaction and earthquake, but it won't go very far. Down here, you've got a strong potential for a flow slide. And what you can do is you can use that type of diagram to explain to people what is going on. So over here, I say, well, that's subaerial thickened tailings. That plots over here. This is subaqueous slimes. They plot down there. And this is a relic subaerial sand beach at another stage in the impoundment. So you can use this diagram to, like I've just done here, you'll find that this is this is software I've provided to you. This is CPT plot 2. You can set over here the depth interval, and you can use the software to go looking at individual layers, and you'll get a little plot on the right. And what I like to do is take these plots on the right and paste them into my design assessment report, because I can then describe what I've identified, what my basis for the identification is, and I can even make some qualitative judgments about the behavior I expect. And that's what I do. Okay, now, up to now, I've been talking to you about how we can identify the stratigraphy at a site and how we can make some judgments about the soil type and even some judgments about its in situ state. We now want to move on to actually let's get the state parameter more precisely. And how do we calibrate? The CPT measures tip resistance, water pressure, and friction. What we're interested in is void ratio, or actually the state parameter. So we have to calibrate the CPT so we can match one to the other. What the calibration, or how it's done, is this thing here. What we have here is, in effect, a very large triaxial apparatus. That's about 1.2 meters, and if I remember rightly, it's 1.4 meters there. And what we do is we place our soil into this chamber in nice uniform layers in a controlled manner. We then stress it. This chamber, as I say, is like a triaxial test, so I can apply a lateral confining stress and I can apply a vertical confining stress, and the two do not have to be the same. When I've got my sand stressed, I can then push a standard CPT into that sand, which is what you see here, and log the data in a normal way. When I do it, I get this measurements you're shown here. This was actually a lateral stress cone where we're measuring the lateral stress on the friction sleeve as well. And what you can see here is when we first go in, there's an effect of the top boundary, and down the bottom, we're seeing the effect of the bottom steel plate. But in the middle here, we have sensibly constant readings. And what we do, we say, aha, I can associate that tip resistance here with this void ratio. And I should say the way we get void ratio is after we push the CPT into the tank, we pull the CPT out, we then disassemble the tank, and we then excavate the sand in layers, and we use a nuclear density meter, the sort of thing you use for compaction control, to measure the void ratio of each layer as we do it. And that's how the void ratio data has come about. And if you take that data, and what I could say, of course, because I know the void ratio, we've actually also taken that sand, we've measured its critical state locus. So I know my confining stress in the tank, I know my void ratio, so I can take that void ratio and convert it to a state parameter. So what I have on here is, and that's my colleague Ken Bean, because he was the guy who cooked up this chamber test. Each one of those dots there represents one of those. And the dot represents the tip resistance we've measured and the confining stress. There, we've done it in terms of mean effective stress, and the number is the state parameter for that test. In fact, it's, to make the graph easy, that's actually minus 0.18 as a state parameter. And what you see is that the contour lines for state parameter are basically radial lines that come off the origin over here. So the slope of those lines is actually the parameter Q. So we just take the Q as each one of those data points and plot them versus a state parameter. You get a line, you get this figure here. It's a very, very simple equation. You get two coefficients, which are sand specific, K and M, but the equation is the same across all soils. And this is how we calibrate the CPT so we can get the state parameter, which is the other thing we need now for the critical state modeling. There have been a number of campaigns of these sort of calibration chambers, and there's a list on the side here. There's been a few more since the slide was prepared, but the reality is, by and large, we're all testing medium sands. It's not as an industry, we do not have a great range of experience in calibrating the CPT. This is the grading curves of what we've done. But even within that limited range, we get very different calibration curves. So these are these semi-log lines. If I go back here, back there, that black line there, and there's some scatter around it, that black line there is now the brown line in there on this graph. Okay, and all these various calibration chamber studies all come up with similar exponential or semi-log lines like we have here. And the problem is this. if you're on a typical tailings impoundment, a not unusual figure you would get for a blow beach sand will be a Q of something like 60. I've drawn this one out. And the problem is, if for your material, something like the Reed Bedford, which is that brown one, or what's green? Can't see it. Oh, Hilton Mine. If that was the appropriate calibration, you'll be a very happy engineer of record because you've got a state parameter of whatever, minus 0.113. That's a very dilatant material. However, if your calibration is more like Toyora sand, you've got a state parameter of minus 0.02, 015. You're actually in flow slide territory or getting towards it. And your decision as an engineer of record doesn't depend on the measured tip resistance, because that's that red line, but on what calibration is appropriate to your soil. And yes, in principle, you could go and do chamber testing, but it's very unusual to do chamber tests for commercial projects. On this slide here, Chet Blackcock, Erksack, and Mildred Lake were actual construction jobs. The rest of them are university studies. And we simply, as an industry, we do not do a lot of chamber testing. So we've got to learn how to use these calibrations and how soil behavior is affecting the calibration. Now, you might say, okay, why don't we use finite element analysis of the CPT? Well, there's a problem. What I've sketched here is a CPT, and I want you to imagine yourself with going down with the CPT and looking out and seeing what's happened to the soil. And what you see is soil going past you like this. It'll be flowing past the tip. Remember, you're going down with the CPT, but it'll be like a fluid flowing past the tip. So you would describe this in terms of velocity and perhaps rotations of that velocity field. You wouldn't use displacement. But that's the problem, because in our geomechanics, everything is posed in terms of displacements. Velocity is what you find in hydraulics. We talk about, velocities in a stream flow. And all our equations that talk about velocity. But in soil mechanics, we've not learned to deal with velocity. So we deal with displacement. And as of today, we still have no direct analysis of CPT. There are some methods coming in called material point methods or the particle point method, where people are beginning to get close to this. But I would say, as a practical engineer, I do not see a finite element program or a program I can put some properties in and push a button. It tells me what my calibration is for the CPT. So how did we learn about properties influence the CPT, and thus how can I learn what my calibration factors are? Well, the chap who got us into this was Bob Gibson, which is the guy you see in the photo. And what Bob did, he said, well, if you push something into the ground, he actually did this work in terms of a displacement pile, when we treat CPT as being like a pile. He said, well, as that thing goes into the ground, it creates space around the tip. And that space around the tip looks a little bit like if I had a ability to go into the ground and inflate a balloon, as it were, I'm creating a cavity. So we have this idea that perhaps inflating a cavity, or the stresses required to inflate a cavity to create space for the CPT, would represent the stresses on the tip would be comparable to the stresses on the cavity. And the beauty of this scheme is that over here we've got a very complicated 3D problem, and everything really should be posed in terms of velocities. Over here, I can do everything in terms of one dimension because it's spherically symmetric, and everything can be done in terms of a simple particle movement because everything moves radially. Nothing gets twisted, nothing overlaps itself. It gets mathematically very doable. So Bob said, well, this is the way forward. By way of background, this methodology was originally developed during World War II for the metal forming. They said we need to be able to understand how we form metals better. But Bob said, well, actually, clay is not that dissimilar to metal, so we can adopt the ideas from metal forming to soil mechanics. And this is what it looks like if you do we expand a cavity and we calculate the cavity pressure. It's that line here. And as the cavity expands, the pressure comes to a stable value. What's happening is, as the cavity is expanding, the area of the cavity is getting progressively larger. So the force to expand it is getting larger, but equally you're affecting more material. And the two processes come into a balance. And that balance point is called the limit pressure. And what we say is, okay, the limit pressure is related to what we see on the cone tip. Now, it's an analog, because that thing there doesn't include shear stresses and it doesn't include stresses here. So Bob did this for what we call Tresca material, or phi equals naught, just straight undrained behavior of clay. We wanted to understand sands and how they behaved. So the lady on the photo is Dawn Shuttle, and what she did, she took Norsand and put it into a cavity expansion analysis, and now we're able to relate critical state properties to the behavior of or the K's and M's of a CPT. And I say it's an analog because you've got friction on the friction sleeve here. In fact, it goes higher up, it goes up the rods, and we have soil steel friction down here. In pink is what we compute with a cavity expansion factor, but we're not including these stresses here. And you might say, well, okay, the friction, I know the friction ratio is only about 1% or something. That's a small number. Well, actually, no, because the friction sleeve is 15 times the size of the tip. Also, the friction goes beyond the friction sleeve. If I compare the friction to the vertical effect of stress, you get a graph like this. That's some loose sand and that's some dense sands, but the friction is comparable magnitude to sigma v. So that means, in effect, you see my sketch here, we have an additional confining stress in the actual CPT compared to what we have in the spherical cavity solution. So we have to get that coefficient. How do we do it? Well, we say it's just going to be a coefficient, like when we do, those of you who are civil engineers and you've done hydraulics, for a weir, we'll have a coefficient of discharge for the weir. So we said, okay, we're going to have a coefficient of CPT, which is this thing CQ, and that's what we're going to compute. And the way we do it is we look back to the chamber tests. This is the data on Ticino sand, and this is the largest data set for chamber calibration tests. Each one of those black squares is an experiment where they put 2 tons of sand in a chamber, stressed it and pushed a cone into it, and they've then reported a Q, which is what gives the vertical axis, and for their reported void ratio, we've calculated a state parameter. So we're able to plot a graph for Q versus state parameter. What we've done is take Ticino sand, we've done triaxial tests on Ticino sand, we've got its critical state properties, the M, N's, and so forth, the Chi's and the H's. We've stuck that into a cavity solution in Norsand, and each one of those black dots has an equivalent grey dot down here. So this is my finite element results down here. And CQ is simply the ratio of the trend line through there to the ratio of the trend line through there. That's how we established CQ. Now, and there is an effect of IR. The reason we have scatter in the finite element solutions, it's not just the state parameter. Gmax actually also has an influence. And what you find, you get a calibration factor that looks like this. This is our K, and this is our M, and they're functions of elasticity. And that's why we want to use the seismic cone in situ, because that gives us our Gmax in the profile. And the computer program that does this a lot, we make available as public domain, is fondly known as the widget. And what that program does is compute Ks and Ms for you. In effect, it's a numerical calibration chamber. Now, of course, you might say, well, we've established CQ for Ticino sound. What about the other sounds? Is it the same CQ? Dawn had a PhD student, Mason Gafghazi, which is this chap here, and his PhD was to look at the world's database and see whether the CQ was the same thing. So what we've done here is we've plot what I call truth. With each of the labs has reported a Q for their test, and they've reported a void ratio, and we've actually tested each of those SAMs to determine the critical state property. So the void ratio turns into a state parameter. So this axis here, I call truth, is the state parameter, which is the void ratio reported by the lab, converted using a CSL, or which we have done by testing that sound in tracks of compression. We then take their reported Q, stick it into our finite element software, and say I can now calculate, using my computed Ks and Ms, a state parameter. So that's what the state parameter here is. And if our methodology is perfect, everything will lie on a diagonal line with a gradient of 1, which is what line of equivalence. And what we find is, yep, everything does lie on a diagonal line of 1, and there's some scatter, and the scatter is about plus or minus 0.04. Keep in mind here that we're talking of testing 2 tons of sand on each one of these data points, and there's a lot of the test I showed you about how we pick a typical QC out of a chamber test. That's the very best test I've ever seen. There's an awful lot of judgments going on in some of these data points, so we shouldn't be that surprised. But on average, we in fact find our procedure for CQ is good. And there are 331 tests on that slide. So that's the case with sand, and that's our methodology for sand. We can take our critical state properties, we can use them to compute K and M values, which allow us to what is usually called interpret, but it's actually more formally would be inversion of the CPT data. The problem we come into when we get to silts, and here's an example of silt data, which is very liquefiable, and this is my Semincor job. And note the very high BQ values, 0.8. There are no calibration chambers on silts as yet. So what do we do with silts? Well, what we did, we said we assume that the spherical to CPT mapping, as I call it, the calibration factor, is the same in silt to sand, because the only difference between silt and sand is the F and the Q's, the ratios change, but the mathematics doesn't. So we said, okay, that's there. We did assume that the pore pressure is unscaled, because there's no reason because there's no extra stresses involved with pore pressure. Pore pressure is pore pressure. And you can check against field data using water contents, but that's not super precise. So I've got one nice case history. But it's the same finite element program. All we do is we just change the pore water modulus. When you use finite elements, you always have a pore fluid. If you make the pore fluid have 0 stiffness, then in effect make it air, you get a drained analysis. If you give it the stiffness of water, you get an undrained analysis. In terms of the Qs, we have this Q times 1 minus BQ plus 1. It crops up again. So we now have Q dash, and that is defined using that parameter grouping. And when we run the widget, we get nice simple trends. The catch being that's for the pore pressure measured at the 1 location. When we measure it at the 2 location, we lose our nice simple exponential or logarithmic lines, and you can see there's a bit of a curvature going on. I have not, and nobody I know has, got an equation that smoothly fits this behavior. So what you have to do is make an estimate of the state parameter range you're interested in, and then take the best fit semi-log line for the state range you're interested in. Now, what I've been describing to you for both silt and sand is fine if you are dealing with sufficient material that you can in principle sample it. And the stuff I've highlighted in blue here, you can see you've got whatever 12 meters of silt. We can easily go and put some Shelby tubes in there and get some of that silt back and get it to the lab, and we can go measure its M and the lambda 10 and all its properties. But what happens up here with these layers are highlighted in pink? Some of those layers are thinner than the length of a Shelby tube. There's absolutely impossible for me, even in principle, to go and sample some of those layers in sufficient quantity to measure the values. And more to the point, I then got to deal with the fact that in situ, my soil type is changing quite rapidly with depth. How am I going to deal with that? Well, this is where we get to the universal method. The idea was that the point-to-point variation of soil property must be sensed by the CPT itself. This goes back to the idea. You remember we were using the soil, what we call the soil behavior type chart, where we could look at what we measure on the CPT, put it onto a chart, and it would tell us what the soil type was. Well, the idea here is, well, with a self-contained method, we can say, well, if we're if we are measuring in say a silty sand, then we can guess some properties of lambda and kappa and whatever, and then we can use those to estimate the Ks. And the idea is right here. Here we have, over here, we find M's commonly about 1.3 and lambda's about 0.05. Down here, M.9, lambda 10 commonly around 0.25. So we can say soil properties vary here. We were previously talking about soil type. We now put a map of soil properties. And that then gives us the Km, and our state parameter goes perpendicular to that. So we have now a universal method. We can use the data from the CPT itself to compute its coefficients. And this is what we, when we first came up with this method, we just said, here it is, and we plotted things up, and we related things to the friction ratio. David Reed, 10 years ago now, looked at a wider database, and what we have is that lambda 10, which becomes kind of a key property for us, is simply the friction ratio divided by 10, and it may be in or out by a factor of 2. So we've got an almost automated method. The only input required is the soil friction ratio M, and you can do that from geological knowledge. Just look at the grain shapes. Are you dealing with sands or silt or whatever? You can estimate M. And it's widely used. You'll find this, it's called the Plewis method. Even in those post-mortem investigations of dam failures, the Plewis method is everybody's starting point. The problem with the Plewis method, it works well, in fact, unbelievably well, 80% of the time. The problem is, at the moment, we do not know any indicators for the 20% of the time where it doesn't work that well. What you can do is you can get some samples yourself and check, where does your site lie in here? Are you high, are you low, or are you in the main trend? And what the CPT plot software does, it allows you to adjust your site to the average trend line. So you can actually do a little bit of tests, and away you go. So we're nearly at the end of the talk. We've got some software for you. The laboratory spreadsheet I was starting and talking to you earlier, it provides synthesis and modeling. It's this NOR-TXL DSS, wherever it is. It is open code VBA. So you can access the code in Excel. If you go to the developer tab and click on the VBA, it should take you straight to the program language itself, and you can see the code. Because Excel treats VBA as a macro, when you open the spreadsheet, you'll have to enable macros or accept macros, okay? CPT plotting and processing, CPT plot 2, you've got, if that's provided to you. This one actually has a user manual. I've taken you quickly through how to use it. Again, it's open code VBA. You can look at the equations and the correlations used. Again, enable macros. The widget, I don't think I've actually given you that now. I'll have to provide that after we finish this talk. That is given both as a source file in Fortran 90 and executables, and there is a user manual for that. My suggestion for you, and the reason I haven't put it up there at the moment, I think you people are quite new to this. I wouldn't worry about precise CPT calibration. Start with the laboratory test synthesis and modeling. Use CPT plot with the Pluis method, which requires very little input, because that way you can start looking and see how well the system works for you. Right, just about last points here. Data archiving, and this is back to professional responsibilities. The dam you're looking at is Duncan Dam. It's in British Columbia, and it's the headwater dam on the Columbia River, which is, I don't know, half a dozen other dams downstream. The river goes from the Rocky Mountains in Canada across the US border, then back into Canada. And at each stage, there are hydroelectric power plants and also flood control as well. This dam was built on a particularly bad foundation. My memory is correct. It had something like 7 meters of settlement when first built. It's on just unbelievably bad foundations. Of course, it was built before liquefaction was an issue. So they carried out in about 1992 very extensive investigations with a lot of CPTs and a lot of lab testing and so forth. And there's a special issue of the Canadian Geotechnical Journal devoted to this dam and the testing, and that's 1994. And I should note here, this dam is owned by British Columbia Hydro, which is a very large utility company. I was asked to do the dam safety review, because dams like this, we look at them every 10 or 15 years to see whether they're still stable or they're deteriorating and things like that. I was asked to do the dam safety review in 2010. All the original data was apparently lost. So here we are, just literally 16 years later, and all the records had gone. And this is a company which has an IT division, which benchmarks things and records things, and everything is gone. All we have is the CGJ papers. And of course, I can't access or process the CPT with new methods because, well, I've got poor quality paper images. So my message for you is archive your data properly and do not rely on the company you're working for. Every job I work on, I take a copy of the data and I keep it on my hard drive. And I would suggest you do the same. You also need to be conscious of how you store it. When I worked for Gulf, we were very conscious about archiving our data, and we had IT systems and stuff moved down to the basement. That was in the days of magnetic discs, and being an oil company, we bought the very best quality magnetic discs, and we archived stuff in 1990, and because the oil price declined, that project was shut down. When the oil price came back in about 2007, we started looking at that project again. So here we are 17 years later, and we got the data back from archive very nicely. No problem at all. We recovered everything. But about 1/3 of the magnetic discs were not readable. The data, they had decayed. We actually archived 3 copies of everything, so we were able to recover most of the data. But my suggestion to you is when you archive it, rather than just relying on leaving it on your laptop or something, burn yourself a CD and put it on, because they seem to last a lot longer, and probably make 2 CDs. So that's it. That's the end of the talk. The suggested reading, I provided 3 papers, and the VGS course notes are probably going to be the most useful to you, and the software is on the start of this talk. it was mentioned it was there, and you're told where you can download it from. That's some user manuals with that. You might want to play with the Traxil one. That's quite a nice video game. But start with VGS notes and then move on to the Traxil. And that's it, guys. That's me finished.
Thank you very much for the very nice presentation.
Sorry, we're out of time.
Don't worry. I don't know what is your availability. Can we stay a bit for questions?
Yeah. We can stay a bit for a bit. Yeah.
Okay. We might lose the translation because we only schedule it for 2 hours.
Okay.
So, but we can answer some questions, and we will have to do it only in English. Very good. Well, and by the way, the recordings of the 2 parts will be available in the SMIG website, so we will upload it very shortly. And on that matter, Michael, we usually ask you to sign like a permit from you to upload the video, so I will be sending you this shortly.
Yeah.
Okay, so we can move to the question. So Eduardo Rojas is asking us, when you use the freezing method to obtain the final void radio of the sample, do you need to make some kind of correction because of the increase of water volume during freezing?
No, because we lock off the drainage valve, so there's no water flowing in or out of the sample, and we don't care whether the sample expands. You're just measuring the water content, and then back on GS times water content.
And we assume that it's saturated, that we verified with the...
That's a key point. It does assume you've done the saturation correct, and you've got a B bar of 0.95 or 0.97 or something.
Perfect. Jorge Guillén asked us, well, thank you for the great presentation. And regarding the interpretation of Gmax, if both laboratory tests and in situ tests, such as SCPT, are available, which would you recommend using to obtain Gmax for use in the NORSAN model?
The answer is both, because in the laboratory you're more controlled, so you might see a better trend with stress level because in situ the soil type and void ratio will be changing. So it's sometimes helpful to pick the exponent out of the lab, because usually we find Gmax will be sigma v or coefficient times sigma v to a power. So the coefficient will vary with soil type and void ratio. So I like to use both, but you'll often find clients will not pay for both; they'll only get paid for one.
Very good. Andres Orozco Flores asks us, why is the dimensionless form of the pore pressure called BQ? What does that mean? I don't know.
The short answer is I don't know why it's called BQ. BQ was suggested by Peter Roth in his Rankin lecture. And what happened, there were 3 groups who independently suggested that the CPT should be, or the piezometric CPT should be analyzed using this formula. And it was Peter who looked at it, because I was one of the 3 groups who said this is the way we must look at CPT data. And Peter said, well, the 3 groups, according to things, different names, we can't have this. We've got to standardize. My proposal is we standardize on BQ. So it's in a Rankin lecture. That's it.
More than enough reason for following it. Rafael Ortiz asks us, could the MOS stamp sampler be used to determine unit weight measurements?
That's a very good question. I don't see why it shouldn't be, because it does cause some disturbance, but the unit weight should be, probably as good as anything else we can do. So it wouldn't be a bad idea to do that.
And Alberto Martinez asks us, what is the spacing between CPTs shown in the 2017 campaign image? What is the recommended optimal spacing for CPT tests in tailings?
Well, I don't have a recommended optimal spacing. It depends on what you're looking at and what your concerns are. And I would also say, which I did when I was talking about this, I don't necessarily think you have to use a regular grid. At Cadia, they went on a regular grid. At Saminkor, we did not because we knew we had a problem in front of the main dam. That's where we knew, we looked from the deposition history. We said that's where, if there's going to be a problem, that's where the problem's going to be. So we put most of our effort down there, and then we just did a few step out ones to make sure we hadn't missed something. So my reply is you've got to think yourself.
Hey, but like I remember that you put in the slide like for the spacing of the analysis section like a quarter of a kilometer, right? Like 250
Yeah,
meters.
that's a number I've seen come up on a number of jobs, and that's a not unreasonable starting point. But again, think about what you're trying to do, where you think the trouble is.
An interesting question from Angel Morales. How does partial soil saturation affect the definition of the in situ state parameter? And what considerations should be made when dealing with soil profiles where suction is acting?
Yes. The short answer of that is that this is a subject of very active research right now. Okay. There's a paper by Carl Smith out of University of Western Australia where he's begun looking at these things, and in effect, what he does, he and his co-authors, they've drawn contour lines in the drained area, and they're drawn contour lines in the undrained area, and then use a linear interpolation over the partially saturated zone. The biggest problem I see with that approach is very easy to define the limit of drain behavior because the CPT tells you if you've got excess pore pressure, clearly you're not drained. The problem comes the transition from partially drained to undrained, and people are looking at that saying, well, okay, what is my CV value from a dissipation test? But I'm seeing a wider range for partially drained than matches my experience. But that, this is something the profession is working on right now.
Yeah, because sometimes, especially for tailing dams in arid climates, you don't get any static pore water pressure, no? You have zero pore pressure, but you have some degree of saturation. You have pore water pressure response, and the usual interpretation, for instance, for the normalized cone resistance is to normalize it to the total stress because you assume that you have zero static pore pressure. But in reality, is negative because you have suction, and what this creates is that this plots the state of the soil in the classification chart up at it should be, and it changed the classification even though the material is the same, granulometry, grain size is the same, and plasticity is the same, and you have clay-like materials, sandy materials telling you the cone because of this partial saturation, right?
Yeah.
Juan Carlos asks us, what are your thoughts about commercial calibration chambers and their applicability?
Commercial ones. Well, what we're seeing now is what's called mini cals, where we take, in effect, a very large triaxial test and turn it into a CPT calibration by putting a very small steel rod into the triaxial test. There's a German manufacturer that sells this stuff, so you can buy one of these things to do that. There are quite a few research groups looking at it. The problem I have is everybody has gone and tested their mini-cal using tailings, silts, slimes, whatever. To my knowledge, nobody has gone and said, okay, if I use Toyota sand, this is what I get. So I've not seen a proof that this equipment duplicates large calibration chambers. People have been allowed to write papers on these mini-cals without demonstrating they can recover standard behavior. So I am, shall I say, skeptical or questioning whether the mini-cal is doing all that's claimed. But undoubtedly, if mini-cal can be made to work, it's going to be very valuable because it's easy and cheap, and we can do lots of calibrations for our individual soils. Maybe we need 20 kilograms in soil. That's good enough.
Very good. I'm going to take the opportunity to ask one myself.
Yeah.
What is your opinion when, for instance, in tailings, when we have a lot of stratification and we have a cone profile that varies a lot vertically? We know that generally the soft layers are the one controlling the behavior.
Yeah.
But what would be your recommendation about the percentile to use when interpreting a very erratic con data?
If right, if you are in a situation where the variation is caused by variation in void ratio or variation in state parameter, there have been two studies looking at this directly. One using computers, and that's paper and geotechnique, and one using centrifuge testing. And the number that emerged is something like the loosest 20% of the profile will control. Is not, if you look at our concrete codes of practice, we would say the loosest 10% controls, or maybe the loosest or the weakest 5% controls. That's too severe for soils. If you do that, you're getting excessively conservative. Some of our codes of practice say conservatively assess mean. Well, a mean is a mean. There's no conservatively assess mean. It's nonsense. But the 80%, if you look at the Tar Island paper, I go into that in that paper. I do not do it with formal, when I was an engineer record, we actually did formal processing. But these days, I just put a line on the graph by eye and say that's my judgment of where the characteristic is. And that's explained in the Tar Island paper. Marcos in Brumadinho, because they were looking at, you'll find in the Brumadinho reports, whether it's the expert panel or the prosecutor, they show histograms of the state parameter. I think that is wrong because if you look at Brumadinho, there's a clear super weak layer that you can see at least across half the width of the dam. So I think you can talk about the 80 percentile in that layer, but you shouldn't be confusing the stuff above it and the stuff below it with the value you assigned. There's clearly a particular layer that causes trouble. And you've got to be careful with statistical processing that you're not averaging out something that is actually a weak point.
Okay. Thank you very much. Jorge Guillen asked us a very long question. I know we haven't covered the topic of numerical modeling, but if you can provide guidance on these questions, I leave them for your consideration. Regarding the use of Norsan in Plaxis, two questions. In the construction of a tailing dam in successive layers, would you recommend using the Norsan model for the initial stage and continuing with Norsan for the construction of the upper layers until the current condition is recreated? Or is feasible to simulate the construction of layers using more column or hardening soil models and then switch to Norsan in the final stage to evaluate liquefaction potential? This question arises because I have observed computational difficulties and long calculation times when Norsan iterates under near zero stress condition, particularly in the shallow layers.
Yeah. What we did at Tar Island, we put the material in as more Coulomb and raised it by 1 meter and then switched to Norsand. So we were doing what the questioner asked, but not, we had a third scenario in the middle, if you will. And it's not just Norsand. Any of these fancy constitutive models run into a problem when the stress state gets near zero. You get divide by zero errors and trapping errors, and the algorithm. Plaxis is actually working on this right now as we speak because they're aware that certainly Norsand, and I think you'll find other models, do not consolidate well in Plaxis because in any finite element program, we actually put on an elastic step and then we look where the yield surface is and we redistribute loads. They have optimized their algorithms for shear failure. And you think of a Traxio test will go quite rapidly to failure in 5% strain or thereabouts. When we do an odometer test to go from 3 kPa to 3 megapascals, can be, if you're dealing with sand, that could be just 2% strain. So we have an extraordinarily stiff system. And the numerical people have not come up with an algorithm which is say, okay, depending on where my load vector is going, depends on what algorithm I'm going to use. FLAC usually does better than Plaxis, but FLAC gets away with it because it actually never solves. It always carries an out of balance force.
Yes, and also there are some situations when you would like to switch to Northern at the end, because if, for instance, you have a very stratified condition with a lot of variation of the state parameter, if you do it by stages, you will have a smooth K-naught consolidation, and you will not capture this variation. So it's better to have some estimation of the stress state and then impose the actual state parameter at the end. Huh?
Yeah, I'm happy with that.
And the second part of the question, when visualizing results, do you recommend defining the potentially liquefiable zone based on the inspection of liquefied points represented by purple triangles, or by evaluating the normalized stress ratio being close to or exceeding 1? This question is based on observation where the stress ratio approaches the stability line, but the point is not marked as liquefied due to a state parameter lower than 0.
No, it's interesting. I've not come across that. I'm not sure what I have to think about this one as to what I prefer to do. Usually we take the limit to chop off lack of liquefaction as a state parameter of minus 0.05, because that builds in a bit of a safety factor. So I would be very nervous to say 0 is a sufficient condition to say not liquefiable. Plus, particularly when you allow for the fact our precision in our methods is plus or minus 0.02, say. So I think, well, the projects I've been involved in, we want to see a comfortable minus 0.05 before we call it non-liquefiable.
Okay, and how are we on time? Do you want to keep going, or we might stop?
If you give me 30 seconds to go and get a beer,
Yeah. Sure.
then we can keep going for a minute or two.
Yeah.
Back in a sec.
So in the meantime, I reminded you that we will have this recording and also the recording from the previous session at the SMIC website. So they will be uploaded shortly, and along with a lot of material that Mike has provided us, some notes, some papers, and and the software that he mentioned during the talk.
Okay, I'm back.
Okay,
I'll have a beer.
now I'm jealous.
Yeah, well, it's 8 o'clock in the evening here, so I'm allowed a beer.
So there's also a lot of congratulations for the very interesting talk. And here's a question of Pedro Reyes. Professor Jeffries, thank you very much for your presentation. I wanted to ask, what is your go-to method for computing the state parameter from CPT data, especially when working with large liquefaction database?
If you're working with a large database, you cannot look at individual calibrations of individual soils. So you're pretty well forced to use the Plewis method, because that relates to what you measured or directly measured with the CPT and will be in your database. I think where you need to be cautious is if one of those case histories doesn't quite fit the trends, then you might want to look into that one in more detail and more formally. The surprise to me, because, well, I have two surprises. The Plewis method is based on effectively knowledge of 1990. That's where the trends were derived. I'm amazed nobody has ever updated the Plewis method or suggested an improved Plewis method. And the second surprise to me is when I look at where the Plewis method has worked, it works just amazingly well. The problem is that we have, I say, 20% of the times where it's significantly out. I just would like to have a diagnostic, and I'd like to see it improved. It was put out as an interesting idea, but nobody's ever said, "Hey, we're going to modify it or improve it."
Perfect. And you mentioned in the laboratory part the method for freezing to get the void radio at the end of the test. What do you think about the Ishihara and Verdugo method? You know that? No.
Um,
The one that so basically they squeeze the sample and look with the volume of water that comes out, and then by squeezing it, then it can be handled without losing water, and then you can wait and get the water content and work out the void rate in that way.
um, I've never, well, okay. Number one, I'm not a lab tester. Okay. My background is the equations and in situ testing. I don't believe anybody used the Ishihara method in the cross lab trial, or if they did, they didn't get in the same bandwidth as freezing. I've heard people complain about freezing, saying it's complicated. From when I've looked at the labs have done it, it really is very simple. We started out, we had to have a cold room, but now we just use a freezer you can buy for $200. Why would you not do it?
Misael Palacios asks us, do you recommend hollow cylinder tests in order to get the critical state line, or it is enough with triaxial test?
What's the alternative?
The hollow cylinder test.
Oh, all right. I love the hollow cylinder, right? But it's a very difficult test, I think, to undertake. There are universities have developed it. They write one thesis and one paper on it, and they then never do it again. So the triaxial test has become the standard, and I'm very happy with the triaxial test because the mathematics can carry us beyond there.
Okay. And perhaps a philosophical question. What do you think about phase transformation? Do you think it's a phase transformation when you have first kind of a liquefaction behavior and then the sample decides, no, I'm going to dilate. So
Yeah.
do you think this is constitutive or this is boundary value issue?
Well, first off, the phase translation is in Norsan. We call it the image trace. That is what we use to drive the model. Okay, so the reason I don't like phase transformation is, and it's sometimes also called the quasi-steady state. The reason I don't like either of those terms, it's not quasi, it's real. And a phase transformation in physics means you change from a solid to a gas. It's just the wrong word. And there's nothing magic about it. Mathematically, it's just a change in a differential term. So it's there in Norsan. This week, the phrase I came up was I called it the image state, because if you look at the mathematical definition of the critical state at this phase transformation or image state, only one of the two equations is met. So you're looking like an appearance of the critical state, but it's not quite there because there are two conditions and you haven't met one of them.
Okay, but from a physical standpoint, do you think it's a constitutive behavior of the material?
No,
No.
it's just part of the stress strain curve. There's nothing magical about it at all. And if you're computing it and where it occurs, if you change the Poisson's ratio, or you change the K, or you change the hardening law, you'll come in a different place.
Okay.
And it's a little bit like undrained strength. Undrained strength is not a property, it's a behavior. That's why you have the phase transition.
Yeah, but I mean, so at the end, it's like so the behavior of the soil is going from contractive to dilative, no? So, and let's say in the critical state framework, you have if your material is to the right, then it's contractive. If your material is to the left, it's dilative, no? So why the change?
Well, that's one way of looking at it. But if you think of the stress to latency plot where we plot eta versus d, it's a straight line. Where it crosses the axis of 0, there's no change in the gradient of the straight line. There
Yeah.
is there is no observable change in material behavior. It's just tracking on the stress to latency line. And the condition d equals 0 is nothing magic about it.
I think I lost you for a second.
Okay. Let me Actually, I won't try and screen share. That's a good one for me to give you something in writing. Actually, if you look at one of the papers I shared, the one on the fundamental nature of the state parameter, there's a figure in that paper which you can look at, and it shows stress to latency, and you'll see where it goes through the so-called phase transition. The gradient of stress to latency line does not change at all.
Okay. There is a question by Erlan Gonzalez. I think he missed this in the talk about the objective of freezing the sample in the triaxial test is to get the final void radio. No? So, there is a question from Hadi. I will leave it on Hadi because I'm not going to be able to pronounce that. Thank you very much for the insightful presentation. A couple of questions. What sample preparation method do you most recommend for characterizing stress and state dilatancy in dense sands? Also, your opinion. In your opinion, do factors such as sample preparation technique, particle angularity, and bedding plane inclination influence the position or shape of the critical state line?
From what I have seen, sample preparation method does not change the critical state locus, nor does it change the stress to latency parameters. What I have seen change is the soil stiffness. In north sand, the property H depends on whether we're dealing with pluviated samples, water pluviated, air pluviated, moist compact. So, and that's not unreasonable. That we all know that critical state models have, or the critical state framework has been derived essentially on remolded soil properties, whether it's reconstituted sands or in the case of Imperial College with the clays, they're just all remolded. So it's a structureless model. Now, if you pose the question, if structure came in, where would structure appear? Well, it seems to me, if I look at the physics, there are two possibilities. The stress to latency property chi, you'd think, well, maybe there's fabrics involved, and that might be where it shows up. But again, in the mathematical derivation, that turns up as a rate parameter looking to how fast we go into the final state. So perhaps not, because fabric would change as we go through it. The second one is H, which is our what controls the evolution of the hardening law. And I've certainly seen an effect of fabric on H, and so I would say yes, that's where I would see it changes the stiffness of the sample, not the rate of change of stiffness. Now, what has also come up, which I didn't put out today, is when you start dealing with things like residual soils, we've got a true structure. We actually have a cohesion involved. If you remember the first lecture where I took you through the Taylor-Bishop strength model, which said there's no such thing as cohesion, and Terzaghi says there is cohesion. Well, you can actually add cohesion to the Taylor-Bishop model. And that's, if you look at the Cadia foundation, that's how that foundation was behaving. So structure was there both on H and basically on M, with M then degrading as the structure got broken.
Perfect. And there is a last part of that question. Will on-drain tests alone be sufficient to identify the critical state line and then use drain tests primarily for the latency characterization in dense sand?
That is where we started, right? With undrained tests for the CSL and then drain tests for M and N and all the other stuff. The problem we ran into was when we start to ask where's the CSL at 1 megapascal, to get a clean critical state at 1 megapascal with an undrained test, we have to start at 10 megapascals. And our equipment can't go there, or most of our equipment can't. There's some rock mechanics labs that can, but so we then started saying, okay, we've got to do drained loose tests to get that critical state out there.
Perfect. There is a question from Angel Morales. When analyzing laboratory test result on undisturbed, in quotes, tailing samples, it is common to observe dilatant behavior. However, when applying methodologies to estimate the in situ state parameter, the results suggest that the material is contractive. What could explain these discrepancies? Could they be due to some sample disturbing during extraction or preparation, or are there other factors that should be considered?
Almost certainly, it's the sample is densified during when you bring it to the lab, extrude it, and then reconsolidate, or then you load it up to your estimate of the in situ stress. We've seen this, we've documented this for Silton in British Columbia, where we had void ratio changes of 0.1, 0.2, and delta R, so very large void ratio changes on natural silts, compared going from what we had in situ to when we got them reconsolidated in the lab. That same mistake was made at Cadia, where the engineer of record took some very high quality piston samples from the tailings, transported them to the lab, and then tested them and declared the tailings non-liquefiable. You can see via videos the tailings were very liquefiable, and the CPT said they would liquefy. So look at Cadia. This is a common thing, but it's because the samples densify during some extent during handling, and certainly during reconstitution or reconsolidation. Just look at void ratio.
Do you think that also when once extracted from the tooth, a bit of loss of saturation could occur that may create some over consolidation?
Possible, but I'm not really sure. I think the bigger thing is when you look at it, there's something called yield in unloading. When you actually unload a sample, you actually cause plastic yielding, and that's why it densifies during recompression.
Okay. And do you think it's the extrusion in the laboratory or the pushing of the tube in the?
It's what happens when the tube comes out of the ground.
Okay. There is a question from Miguel Diaz. According to your experience, it is recommendable to calibrate the state parameter from the CPT or from triaxial tests for tailings, or should I use other tests?
My procedures has been properties come from triaxial tests, and then we pull the in situ state off the CPT.
And what do you think about these approaches based on poroelasticity to get the porosity or the void ratio with the shear wave velocity? Like the FOTI approach.
The problem is it's a weak relationship, right? If you look at the fundamentals of shear wave velocity, there is a dependence on void ratio, not a dependence on the state parameter. It's strictly void ratio. So in principle, you can say if you maybe normalize the shear wave velocity, you might begin to get the state parameter out of it, or an estimate. But it's in mathematical terms, it's a very ill-conditioned relationship. So I would not do it.
Okay. The last question, we managed to finish all of them. Santiago Guivin Zamoran is asking, are there any other methods besides freezing to accurately determine the final void ratio?
None that I know of. But again, you got to remember, I'm not a lab tester.
Perfect. But I think that's everything. A lot of congratulations, and and
No.
regards from a lot of parts of the world.
Right. On that note, then, I'm off to get my second glass of beer.
Very good. Cheers.
Yeah. And thank you, guys. And thank you for listening. It's been entertaining.
Yeah, yeah. Thank you very much. We really
Yeah.
appreciate your time, and we hope to have you here, maybe in person sometimes. It will be nice. We will try
Okay.
to convince you.
Sounds good. Bye, everybody.
Bye.